Good morning. I shall be talking today on obtaining carbides, nitrides of silicon from polymeric precursors. But before that, let me step back in time and see why this has become very important. All of you have seen the picture, the space shuttle in various forms. These black tiles which you see over here, these are basically at the nose cone, at the bottom. What are these tiles? These tiles are fundamentally made from silicon carbide. They are black. They are also made from graphite. Depending on their area of use, on the space shuttle, they use somewhere carbon tiles, which are very refractory. At places, silicon carbide tiles are also used. Now, silicon carbide is a material which is very abrasive. Lot of you see sanding papers, that is the papers with which they clean walls before painting. The cheaper papers are made from sand grains stuck on a hard paper, but the more expensive ones, especially those that are used to clean the surfaces of metals, they will have a black powder deposited on a paper and they are stuck by glue. These are silicon carbide powders. Silicon carbide, as I will come to it, has many application areas. This silicon carbide is basically has different crystallographic forms as given by beta carbide, alpha, beta, this silicon carbide, high temperature silicon carbide, and these are available if you are looking carefully in Wikipedia. So, I do not need to go over this, you are intelligent enough to read it up. This silicon carbide is principally made, it is given over here. So, I will maybe jump quite a few things. Wait. Okay, again find it. So, let us forget it. This silicon carbide is made by mixing silicon powder with carbon, forming it into a shape. Let us say for simplicity's sake, let me draw a rectangular shape. This has got silicon powder mixed with carbon, and then it is dipped into a molten silicon bath. This is molten silicon. The silicon, molten silicon seeps into this body, reacting with the carbon to give you the silicon carbide. Now, there are various processes of forming silicon carbide. This is one process. There is reaction bonded silicon carbide, all of which you can find, whose reference to which you can find in this particular paper, in this particular Wikipedia article. Silicon carbide by itself has a huge range of uses. As an abrasive, I have already talked of sanding. These are hard cutting discs which are made up of silicon carbide. This is also used as personnel bulletproof vests. You can read up all of it. There are automobile parts, and now you have got ultraviolet silicon LEDs. One thing that I do not find over here is silicon carbide as a sensor. You see, in steel making, hydrogen embrittlement is a major problem, and measuring of the hydrogen in the output gas of the blast furnace or the secondary Bob furnaces is very important. The only material which can withstand those high temperatures is silicon carbide, and silicon carbide has been used as, or is being developed for use as hydrogen sensor for such purposes. I talked of in the lecture that it was written carbides and nitrides of silicon. So now let me talk of silicon nitride. You will have a lot of synthesis methods given over here. You can take silicon and silicon. This is, say, a shape of a silicon powder, shape made from silicon powder. As you can see over here, react it with nitrogen and you get silicon nitride. You can get the various processes, silicon tetrachloride to silicon nitride over here. From sand to silicon nitride, there are processes. If you are looking for electronic grade silicon nitride films, you have got silane being reacted with ammonia. I had referred to this earlier. Silicon tetrachloride reacting with ammonia. These methods I had referred to much earlier. The advantage of silicon nitride is, you can see, typical conventional ceramics have a small tensile strength. However, silicon nitride has higher tensile strength, and hence, for example, it is being used already in the automobile industry, in the bearings, especially very high performance bearings. It is being used as a thruster because it can withstand high temperature and a huge range of applications, which you can look over here. Here, silicon nitride CVD process for developing circuits is given over here. Now, in all these cases, what we have is silicon carbide or nitride in the form of basically grains or a thin film or a hard body. You have seen the space shuttle's picture. The white areas of the space shuttle, they are made from fibers of silicon dioxide, making the processing of those much easier. But if it was silicon carbide, and silicon carbide could be fabricated in the form of fibers, it would have been very wonderful, so that silicon carbide or silicon nitride could have been used for various other applications. I had talked to you of alkoxide based sol gel processes for fabrication of fibers of basically SiO2 based materials. This lecture focuses on synthesis of carbides and nitrides of silicon not only for purposes in bulk or coating, but also for basically being used as fibers. So, let us take one by one. How can we synthesize these silicon carbides and silicon nitrides? You see, in tetraethyl orthosilicate, I started off with and did the processing so that I landed up with this sort of a structure. In silicon carbide and nitride, the point is, how do we get this sort of a structure? For example, the very first ones was from this, linear polysilanes were synthesized. So, this material was reacted with sodium in benzene medium, and what was obtained was this polymer. Essentially, what it means that we got this sort of a linear polymer. Now, this is called polydimethyl silane. And the problem with this is it is very, very, very insoluble, and it decomposes at 250 degree centigrade to form polycarbosilane. But the point is, in spite of lack of solubility and the fact on decomposition it forms polycarbosilane, may say this is a process which does not yield a polymer of silicon carbide which is processable. But I shall later on in a few minutes use this process to generate silicon carbide. But before I go to that, I would add a little bit of twist to the tail in this particular one. For example, I had here Cl, Cl, CH2, CH3. You see, here one of the biggest problems is that I have got a linear polymer. Whereas in TOS system, I had got a branched, cross-linked SiO2 link. So, here the fact that it gives only a linear polymer is also a major problem. So, we need hyper branched carbosilanes. there were many problems in synthesis of these hyperbranch carboxylanes. Is that during subsequent thermolysis, because you realize that after this polymer it will be heated under inert atmosphere to decompose these methyl groups and get SiC, whatever. Now, during this reduction process, what are the biggest problems of getting any hyperbranched polymer? Because you may argue, hey, if this decomposes, then why cannot I get that is, each of these carbon atoms would then branch with more. So, the question is, why is it that I am saying that this is a linear polymer and this is almost useless? But surely you could argue back that each on thermal decomposition, each of these carbon methyl groups would cause the formation of this sort of a carbon one, and it could easily hyperbranch. The difficulty is there was incomplete reduction always. That is, this reduction was always incomplete. And what we had was a complex mixture of products which were of no use to us. The first case where this was overcome was when this sort of a material this sort of a material was available. Now, in contrast to the previous linear polymer, this is soluble in water. And this gave the first break of being able to generate silicon carbide fibers, though this did not progress much further. Before I go on to the actual how silicon carbide is, and before I go on to that, what I would say is there are various processes which are possible. For example, I talked of this particular process. Let me see. So, here I have now been able to put to this particular process the R bit linking the SI, the R linking the SI. So, this would allow me to form the SI C sort of groups. But however, the problem that happens is in this particular case, this particular reaction is basically catalyzed reaction, a very catalyzed reaction, and these complexes are very, very unstable. That is one major problem of this process. So, how was this overcome? So, now let us talk of polycarbosilanes. Basically, these are the precursors for high modulus silicon carbide fibers. In contrast to polysilanes, polycarbosilanes have polymer backbone, which are composed of silicon and carbon atoms. So, the first thing that we realize is if we try to replicate the alkoxide chemistry, we were never linking up with SiC. Yes, there are methods of obtaining SiC, but the difficulty is that these processes are very unstable processes. Process control is very difficult and the polymerization steps are not easy. In carbosilanes, what we have is, we have got alternating SiC arrangement. The best example of making these SiC using organic route is basically the Yajima process. For example, I will come back to the original thing. Remember, I had started off with this and landed up with a linear polymer. Let us modify this process a bit. Again, I am reacting with sodium, getting sodium chloride out, landing up with exactly as before, but now I am going to heat it at 400 degrees centigrade. The resultant product is and voila, we have got SiC. So, now here we can have SiC something which we failed to get through this particular process. What happens over here is a bit of organic chemistry, but I guess today, where it is a bottom up approach for most materials, that is starting with the molecules and going up, means organic synthesis, it is worth looking at the process. This rearrangement, what would happen that is this material A When it is heated at 400 degrees centigrade, the first thing that happens is this. This one reacts with causing rearrangement. To give you this particular one. This particular SiC chain. This is called a Kumada rearrangement. This is called a Kumada rearrangement. These compounds, this SiC or the polycarboxylanes, can also be, though it is a process which is not followed due to low selectivity, is from the halides. React with sodium, sodium bromide is released, and you have this polymer. But the problem is there is very, very low selective. However, there will be very low selectivity if these are methyl groups. However, if these methyl groups are changed to phenyl groups or C6H5, or basically using this phenyl group, then what we would land up with is And this, when reacted with HCl-AlCl3, now this is a standard organic reaction. What we get is this particular material. And then if this is reduced with LiAlH4, we land up with this particular material. This is polysilyl methylene. So what we have had over here is silyl diphenylene. We reacted with sodium and methyl bromide. We got this particular compound. Then the standard reactions with HCl-AlCl3 and LiAlH4 gives us this polysilyl methylene. The advantage of this is that it is soluble and its pyrolysis, I'll come to this pyrolysis part later, yields about 75% Si the silicon carbide. One of the things that has to happen over here is during the pyrolysis step, the amount of conversion to the carbide is very important for choosing any particular step. Not all steps give the same amount of silicon carbide, which I said in that case was as high as 75%. You see, yet, with an yet, this was polysilyl methylene. I said this is polysilyl methylene. However, if I had used polysilyl ethylene, one of the biggest problem is that the reaction takes very, very long. There is reduction of this to give you the silicon carbide takes a very, very long time. This was avoided by using solvents like furan. The solvents like furan helped in forming the SiC. Now, having talked of how is polycarboxylanes, like say polysilyl methylene was formed. Now, let me see how I can convert them into silicon carbide ceramics. So, let me use a Grignard reaction for the purpose. Phi for phenyl group. This is basically SiCl, Cl, benzene, CH3, this particular compound. What would I get? I would get this. Now, this when treated with HCl, AlCl3 and LiAlH4, one after the other, what we land up with is now, this is one way of obtaining SiC linkage. Now, when you pyrolyze this under vacuum or rather inert atmosphere, you can get silicon carbide. But the advantages of these materials are they are soluble in a solvent. So, what you can do is dissolve these polymers in a suitable solvent, then draw fibers from it. There are various standard techniques available for drawing fibers from polymer solutions. Get the fibers, pyrolyze them, and you got silicon carbide fibers. That is the advantage of this particular method of making silicon carbide from polymeric materials. But as I said, but as I had shown that at least in one case I had shown that the material was where was it gone? Yeah. In this case, polydimethylsilane, I do not get SiC link. 2, it is insoluble, and hence it is useless for us. So, the biggest thing for silicon carbide fibers is having the organic chemistry right, so that we have got SiC link and have polymers that are soluble. There are developments where this material is perfectly soluble. Once dissolved in the solvent, it can be drawn into fibers, and those fibers can be pyrolyzed to give you silicon carbide fibers. There is a lot of literature which you can read up over there on this, and well, you can have there are various synthesis processes, most of which are patented, and I am unable to bring them up due to proprietary rights restrictions. Because today the patent regime has changed. What we could do 5 years ago, we cannot do anything anymore now. Now, let me come to precursors for silicon nitride. As you had seen, silicon nitride is a ceramic which has got a huge importance, and this being able to fabricate silicon nitride fibers has been a major goal. One of the ways it can be done is the Si and Si link. And when this is pyrolyzed in an inert atmosphere, you get silicon nitride. Since this polymer is soluble, getting silicon nitride fibers, it has also been made possible due to the very fact this polymer is soluble. Now, let me go to now synthesis of Si3 and 4 SiC composites. Why am I going to do this? If I draw a triangle, a three-phase diagram sort of, yes. Generally, in such composites, the phase of silicon nitride generated is on this particular tie line. At temperatures greater than about 1484 degrees centigrade, decomposition occurs, and this has been a major problem of synthesis of silicon nitride, silicon carbide composites. However, let us see, there are reactions which makes it possible to have such silicon nitride, silicon carbide composites if we use the organic chemistry very well. And further, if I take the ammonia out from here again, what I am going to have basically, that is and I have landed up with silicon, nitrogen, silicon, carbon, silicon, nitrogen, carbon bonds. Another way is to do this. React with ammonia, and what you get is this is how I get silicon, nitrogen, silicon, nitrogen. Now, these materials are all soluble in water, soluble, and hence they are easily processable in the form of fibers. Another interesting one I would take up is silicon, boride, carbide, nitride fibers. Why did I take this up? Because these are much more refractory than the others. So, in this particular method, there are a variety of processes which you could adopt, synthetic techniques which you could adopt for making this silicon, boride, carbide, nitride polymers. Essentially, you see this, all these pre-ceramic polymers which I have talked of today, they can be used for, they can be molded, shaped, coated, spun, even chemical vapor infiltration can be done with these pre-ceramic polymers. And on heating, what we get are bulk ceramics, we get fibers, which was why I went into this whole lecture, fiber matrix composites, so now by this process you can generate silicon carbide fibers and you can have far better SiC Al2O3 fiber matrix composites, porous media, obviously, because you take these silicon carbide fibers, weave them, pyrolyze them, and you've got a very big porous media. This is very important. Ceramic joining, ceramic joints, yes, ceramic joints. So, these synthesis of silicon carbide nitrides by the polymer pre-ceramic routes help us in obtaining these huge areas of materials, especially the fibers, which allows us to have high temperature refractory ceramic carbides, nitrides or SiBCN into shapes which are easily handleable. Today, the space shuttle, which has now gone out of commission, something new will come up, but in the final stages they had refractory linings which was in the form of a cloth, which they would simply staple by means of titanium pins on the surface for repair. So, maybe in the next space missions where high temperatures will be required, silicon carbide, silicon nitride or silicon boron carbon nitride fibers will be developed for having such reusable spaceships. Thank you.